Hello everyone, my name is Adebayo Motosho and I'll be making a presentation on detecting return-oriented programming on firmware-only embedded devices using hardware performance counters. So this is me in the picture and my co-authors, and we are all from the University of Passau. So let's begin. Code reuse attack is one of the most dangerous software security exploits, and it describes classes of attacks that work by chaining together small pieces of instructions called gadgets to craft a payload which can then be used to exploit a software vulnerability, which is usually a memory bug. Therefore, instead of injecting a new instruction, newer ones are created from existing instructions in a program code base. Generally, an attacker selects only a small subset of the existing instructions to pass a new command to a running program. This new command can then be used to circumvent a device or an application's security and then make a device to perform an unintended operation, such as illegally accessing or unlocking a backdoor that would normally require a permission to access. A very popular strategy for joining gadgets and reusing code is the return-oriented programming. The concept of return-oriented programming is not new, and it has been widely studied in typical computer systems running operating systems such as Windows and Linux. But little is known about the behavior or the detection of this kind of attack on resource-constrained devices without an operating system, but only a firmware that runs directly from the flash memory. Therefore, in this paper, we present attacks orchestration on embedded processor. We also present the first detection on firmware-only embedded devices using hardware performance counters. And lastly, we present hardware performance counters that can serve as indicators of return-oriented programming attack and its variants called jump-oriented programming on an embedded processor. For the purpose of this study, our target processor is Xtensa. Xtensa is a Tensilica processor platform manufactured by Cadence. It is a reconfigurable processor that is targeted solely and optimized for embedded devices by allowing the use of specialized instruction sets called Tensilica Instruction Extension. The Xtensa Core LX family includes LX106, LX6, and LX7. LX7 is the latest in the series, and it is our processor of choice. Xtensa is popularly used in audio and voice digital signal processors, and it is present in a lot of Internet of Things and Industrial Internet of Things. Despite having specialized instruction sets, this does not protect Xtensa from memory bugs that could result in a code reuse attack. For example, these are some recent attack CVEs found on MediaTek digital signal processor using Xtensa chip. As we can see, majority of these bugs are due to incorrect bound check, which allows an attack to exploit memory vulnerability, such as a buffer overflow or a heap overflow. And these are the kind of vulnerabilities that were exploited in our experiment in order to reuse code in a firmware-only environment. But before demonstrating how this exploit works on Xtensa, we should briefly take a look at Xtensa's instruction set architecture. Generally, Xtensa's instructions operate from right to left, except when using the store instruction. The load and store instructions are two important operands in Xtensa's assembly that perform push and pop operations when manipulating the stack. The first two lines in the assembly of a function represent the prologue, and these instructions set up the stack, while the last three lines is the epilogue, and it deallocates the stack and restores program control flow. So here are some important registers in Xtensa. The register A0 stores the return address, the A1 is the stack pointer, and function arguments are stored in register A2 to A7. But if a function has more than 6 arguments, the remaining arguments are usually saved onto the stack. Callis arguments are usually saved in register A12 to A15. A ROP gadget in Xtensa ends with a ret instruction, while a job gadget ends with JX instruction. It is also possible to use collex gadget to perform a jump operation, as both of them basically perform similar operation by jumping to an indirect address stored in a register. This is sometimes called call-oriented programming. We also have a special type of jump gadget called dispatcher gadget. This type of gadget is usually used to link together multiple jump gadgets so that each of them can be called sequentially. Now that we have some information about Xtensa instruction set architecture, let's look into the detail of how ROP works on Xtensa. Assuming this is the memory layout on our device and we have the code section and the stack section, the stack is usually not executable, but the code section is. Also, the stack grows downwards and our 15-byte buffer grows upwards in the opposite direction. So, if bound was not checked and an attacker fills the buffer with malicious inputs greater than 15 containing the addresses of gadgets in the code section, this can force the device to execute sequences of instructions that were neither originally called by the device nor meant to be executed in the order specified by the attacker, but can achieve attacker's intended purposes. So basically, in this example, the return address is overwritten and the program control flow is hijacked and the addresses of three gadgets 1, 2, 3 are written onto the stack. Because the stack is a last in first out data structure, then gadget 1 is executed followed by gadget 2 and gadget 3 using return instructions. The program or the device will likely crash after executing the last gadget because we have been working on a corrupt frame. However, it is not impossible to restore to a non-crashing control flow, and this will make the attack even more difficult to detect. Scenarios such as this are considered in our case. Now, here are some of the challenges of detecting or mitigating code reuse attack on firmware-only embedded devices. These devices have neither a real operating system nor a fine-grained privilege separation and execution isolation that are available in a conventional operating systems, but only a firmware that runs directly from the flash memory and performs only manufacturer's predefined set of tasks. Therefore, an attack usually targets a firmware function instead of a shell which is not usually available. Therefore, being resource constrained, sophisticated executable memory protection techniques such as address space layout randomization are not supported due to the lack of a memory management unit. In addition, an attack is difficult to implement on them without some initial knowledge about a firmware function to be exploited. And there are a few ways to gain this information. For example, through sniffing of an unencrypted incremental update by an attacker. Our ROP detection methodology employs hardware performance counters and machine learning. HPCs are special purpose registers that can be used to capture microarchitectural changes when a program behavior is modified, and they have been proven to be cost-effective approach for malware detection in non-embedded processor with a very high accuracy. Although there are no HPC standards and they are manufacturer dependent, for example, Xtensa has 8 hardware performance counter registers that can be read simultaneously, 30 events and 125 sub-events. We programmed the Xtensa performance monitoring library to have access to these low-level events. We also sampled the HPC capturing over wide corpus of cycle to provide us with sufficient data that best represent the behavior of a program under an attack. We found that for any given program, the higher the frequency or the clock cycle of reading the HPC, the lesser the number of HPC data that are captured. So we need data in order to build our detection system. This is the experimental setup for capturing the hardware performance counters microarchitectural events that were triggered as data when the program runs on our Xtensa configuration. Also, we use an FPGA running an Xtensa LX7 configuration because as at the time of carrying out this study, Xtensa LX7 was not available in the market. Our training programs are interrupt driven and they follow this code flow, which enables us to get fine-grained HPCs that represent both attack and benign behaviors. And we did this solely for the purpose of training our detection system. It is also interesting to know that the HPCs are deterministic, and this is likely due to the fact that embedded systems perform repeatedly manufacturers' predefined operations and therefore have predictable behaviors. This is an example of a payload that includes not only the addresses of gadgets, but also the parameter to be passed to a firmware function that is being exploited. The parameter here is A2 in hexadecimal, which is 162 in decimal. This kind of value and even a larger number can be used, for example, to make a device to maliciously perform an operation repeatedly and to store the device, and possibly lead to a denial of service on the device.
So after exploiting several similar payloads on instrumented programs running on Xtensa, HPCs were collected in order to measure and verify how well this approach can detect code reuse attack on Xtensa. We developed a binary classifier and evaluated it based on two questions. What are the top HPCs that could be simultaneously read and that could indicate the patterns of code reuse attacks using ROP or job on firmware functions running on Xtensa? Also, at what precision and recall can a binary classifier predict this kind of behavior using the proposed hardware performance counters event? The initial data shape consists of 30 features, which was further reduced after feature engineering. Afterwards, we evaluated over a couple of machine learning binary classifiers, and support vector machine gave us the best accuracy. However, SVM is an excellent binary classifier if data is balanced, but because the number of positive cases in our dataset are less than the number of negative cases, with about a factor of 7, we therefore use a weighted SVM. The weighted SVM modifies the SVM penalty parameter to fit the model for each instance so that the weight is proportional to the class distribution, and this helps to reduce model bias. The high ROC score shows that our model has a good predictive ability. Also, as the number of exploited gadgets increases, the number of CPU cycles also increases.
So to evaluate our model performance against random programs that run on Xtensa platform, we extended and recompiled some of the embedded benchmark programs in my benchmark for Xtensa. This is because the programs in my benchmarks were built for ARM processors. In these programs, we randomly exploited ROP chains containing 1 to 6 gadgets. This table shows the distribution of the number of codes or gadgets that were reused in each of the benchmark programs and the complexity of each of the programs, as this was useful to us during detection analysis. The top 8 simultaneously read HPCs used by our model are committed instructions, branch penalty cycles, count cycles, pipeline interlocked cycles, data memory store instruction, data memory load instruction, exceptions and pipeline replace, and data TLB accesses. Therefore, with these hardware performance counters, our model gave the following precision scores on the 10 benchmark programs, and from the exploitation of these 10 programs, we obtained an average precision of 86%. Since precision is the accuracy of positive prediction, this means that our model can make positive prediction with 86% accuracy. Furthermore, we computed the recall matrix, which is the ratio of positive instances that are correctly detected by the classifier. So, on our benchmark programs, we obtained an average recall score of 70%. This implies that at least 70% of the positive cases are correctly detected. We noted that it is not just the number of code reuse or the number of ROP gadgets that influences ROP detection, but also the complexity of the program being exploited. At the same time, we have shown that hardware performance counters can actually detect code reuse attack on firmware-only embedded devices that have these special registers with significant accuracy. This brings us to the end of the presentation. Thank you for listening.